Okay, fantastic. We're ready to get started. It is 4:15, and I'm really looking forward to this session. I often don't get an opportunity to do level 400 sessions, and they're my favorite thing. So I do hope if I do my job well by the end of this session, your head's going to be hurting. You're going to have seen a bunch of stuff that you don't understand. That's kind of the goal. So before we get going, so hi everyone, I'm Ben Armstrong. I am a program manager who works on the core team at Windows. So spend my day working with the engineers, working on kernel, core virtualization, hypervisor, and over the last couple of years, containers. So before I get going, just want to do a show of hands. How many people here have played with Windows containers? Fantastic. That's about a quarter of the room. I do want to highlight for the other 3/4 of the room, you've turned up to a level 400 session for a technology you haven't used. This is going to be a bit rough on you. Hang in there. How many people have played with Linux containers? Okay, about half the room. So that's great. There are a couple of slides here where I'm going to be talking about how this compares and contrasts to Linux containers. I'm going to do a very quick high-level setting the stage. Do a very quick intro demo because I expected that there were going to be a bunch of people who hadn't played with Windows containers, and then we're going to go off into the weeds very quickly. So let's get started. So why did we build containers? Why did we do this? So we've been working on containers for a number of years now, and the long and the short of it is that while virtual machines are the foundation for cloud, you can't do cloud without virtual machines, we didn't actually build virtual machines for cloud. When we built virtual machines, the concept of cloud didn't exist. We built virtual machines for a world of physical computers, and we modeled them after physical computers. And they've been a great stage for bringing the idea of cloud computing together. But they weren't designed for it. And so really, with containers, we took a step back and we said, OK, what does it take? What does it look like if we build a virtualization concept that is tailor-made for cloud operating systems, for cloud patterns that we see? And as I go through this, there are going to be a couple of things I'll call out and say, look, here's a pattern in which we did something completely different because we built this for a cloud world. So what do containers bring to the party that make them better for cloud? There's a whole bunch of things, and I've got a bunch of slides up here, and if this was a level 200 session, I would spend 10 minutes talking through all of these. But because it's a level 400 session, I'll say from the engineering point of view, there were really 3 things that we focused on. And all the work that we did and all the engineering effort that we did was basically the argument and the friction between these 3 points. The first point is that containers had to be fast. They have to be fast to deploy. They have to be fast to destroy. They just have to be blindingly fast. Because in a cloud world, taking 5 minutes to deploy a virtual machine is too long. That's a really interesting thing to think about. To highlight, when we first came out with virtual machine technology, we would talk to customers, and they would tell us, I'm sure many of you can remember when the world was like this, though you'll be like, man, I've tried to forget. 15 years ago, a developer would go, I need a web server. And the IT department would go, we're really good here. We can have you one in 6 weeks' time. Because it would take 6 weeks, because you had to order the hardware. The hardware had to arrive. You had to stand it up. And in that world, the fact that virtual machines took that 6 weeks and brought it down to an hour, fantastic. But in a cloud world, no, not good enough. So speed. Speed was one thing that we really focused on. I'm going to spend a bunch of time talking about that. The next thing that we focused on was reliable portability. What I mean there is, as we see the evolution of cloud, we see people using multiple clouds. We see the rise of hybrid cloud. We see all these patterns. And one of the things that's really critical is that you have to be able to build it and use it on your infrastructure, on your cloud, pick it up, easily move it somewhere else, and have it be not just quick, but reliable and reproducible. So that's the second thing that we focused on. And the third thing we focused on was, newsflash needs to be able to run the apps that you have. So compatibility. So being able to bring the code that you have, the apps that you have, the platform that you have across and run it in containers. So that's kind of the trinity of things we focused on. And from an engineering point of view, all three of those things step on each other's toes. So we spent a lot of time working through the details there. So let's talk about performance. And there's going to be a lot of things that, as I talk through the architecture, I'm going to point out and be like, we did that for performance. So where are we on performance? The short answer is crazy fast. So the numbers we have here, this is actually done on just a HP server, a fairly standard rig. If you look at this, the top box is Node.js with Nano Server, under 600 milliseconds in a Windows Server container. So I want to be really clear on this, and this was put together by my team. I'm a bit grumpy about this slide because the virtual machine number is misleading. The virtual machine number is how long it takes to boot up a pre-configured virtual machine and get Node.js running. The container number is how long it takes to go from nothing to a new container deployed, booted, and Node.js up and running and responding to workload, 600 milliseconds. That is mind-blowing. Similar, obviously, if you use Hyper-V containers, Windows Server containers, there's a lot of different accesses here. Similar to performance is density. Amazing amounts of density changes here. Once again, Node.js Nano Server, first container that you start, 120 meg. Additional containers, 75 meg. A little story on this page. But before I give this story, two things to know about this technology and me working in this space. The first thing is people come to me all the time and are like, what's the future of virtual machines versus containers and so on? And I do want to be very clear, the future of virtual machines versus containers is hotly argued on the core engineering team. So if anyone tells you like, oh, this is the future of virtual machines versus containers, they're making it up. We have people on the core engineering team who are like, oh, we believe one day it'll be all containers. We have people who are like, oh, it's going to be a mix of virtual machines and containers. We even have people who are like, virtual machines and containers. No, we're going to build something new. So this is something that's hotly debated. But one of the things that really kind of riles me up and makes me go like, grr, is when I talk to people who've been looking at containers and they're like, oh yeah, I can see using this for dev tests and for new cloud apps, but I don't imagine that I'll ever use this for my core infrastructure. And I go like, I see it going like, no exaggeration, in my house, I have a DHCP server that's using 1 gig of memory and 20 gig of hard drive. What the heck? Like, that should be using 100 meg of memory. Same for an FTP server, same for a DNS server. There's like so much resource that's wasted in my infrastructure. I mean, yes, it's a lot more efficient than when we used to do it on physical computers, but we can do so much better. So I'm going to quickly jump across. I'm going to do the demo a little bit earlier than it is in my deck. So I'm going to switch across. All my demos I'm going to be doing in a virtual machine. This virtual machine is running Windows Server 2016 core. And I just want to do first some quick basic demos of using containers. I'm going to zoom in a bit so we can all see the text a bit better. So this is, if I type in the right window. So I have no containers defined right now. I have 3 images. I have the Windows Server Core image, the Nano Server image, both of which are from Microsoft. I also have an IIS image that I've built that I'll show you in a little bit. And I'm going to do this first command here. And what this command says is it says, Docker, can you run a new container? The --rm says, delete it when you're done because Ben's doing a demo and he doesn't want to remember to have to delete it later on. Use the Windows Server core image and start the command prompt. So we're going to go ahead and do that. And in about 2 seconds, there we go. And that has just created and deployed a new instance of Windows Server for me. That fast. It's got its own IP address that's separate from the host, and it's got its own computer name. And so I can exit out of that, and that container gets thrown away. So incredibly fast. Similarly, this command says, OK, let's create another container. This time, let's use NanoServer. And instead of running command prompt, let's run PowerShell. This is the easiest way to deploy NanoServer. I'm going to be doing NanoServer session on Friday. But here we go, new system. And once again, it's got its own IP address, own system identity, all very quickly deployed. So that's kind of the power of containers, is just this speed, lightweight, and agility. So let's jump back. And trust me, we'll do more complicated demos. Interesting is up to you. We'll do more complicated demos later on. But I do want to take a moment to talk about Docker, because I just used the Docker commands to create those containers and get this up and running. So there's been a lot of confusion about what Docker is, what Docker isn't, and what our relationship with Docker is in this space. So the first thing to talk about is Docker is not containers. It never has been. Docker is a great management engine and experience for using containers. Now, the fun story is we started working on Windows containers. We'd been working on them for a bit. Docker was becoming more popular in the Linux container space. And we kind of got to the stage where we were like, OK, we're going to announce that we're working on Windows containers soon. We should be nice people, and we should go down and meet with the folk at Docker and say, hey, we're working on Windows containers. And honestly, our expectation was that we were going to meet with them, and they were going to say, that's nice. We don't care about Microsoft. Go away. And we're going to, fine, and walk away. Instead, when we went and met with them, they said, that is fantastic. We know we need a solution for Windows, and we had no idea how we were going to do it ourselves. Please work with us to have a great story for Docker on Windows. And so we did. So a couple of key things to call out is we haven't forked Docker. We haven't done some sort of Docker compatibility layer. We have actively contributed to the open source project. And when you run Docker on Windows for container management, you are getting, it's built from the same source code that Linux Docker runs on. And the great thing about that is, right now, there's a whole lot of work going on out there building different tools and management stories that sit on top of Docker. And all of those just work out of the box with Windows containers. So anything that you see where it's like, oh, yeah, this supports Docker, also works with Windows containers, which is fantastic. But here's my first of many block diagrams. Let's talk about what this actually looks like under the covers. So I mentioned we run Docker. It's a management engine for containers. And containers is a base functionality in the operating system. Now, when you actually sit at the command line and type in your Docker commands, you're actually running the Docker client all the way up on the top left. And I can't see my pointer. There we go. We're running the Docker client. That talks to the Docker engine, which we have running as a Windows service. And it talks to the compute service. This is a new service that's in Windows 10 and Windows Server 2016. You can go looking around. There's the Hyper-V compute service. And the compute service provides a nice, simple low-level API to create and manage containers. This is actually publicly accessible. If you are of the length that you want to go out and build your own alternate to Docker, and there are some people who do. We actually have some great open source examples on how to use this API. So I've got 2 links there. The first one is actually a wrapper that we put together. It's a C# library that talks to the host compute service. We actually put that together because we had a bunch of research teams inside Microsoft going off and building their own APIs to the compute service. And we were like, guys, stop wasting your time on that. Let's just put one together that everyone can use as a sample. The second one here is the HCS shim. That's actually the library that we use ourselves for our work with Docker. But if you want to understand, at an API level what this looks like, then you can go have a look at those 2 projects. Here's my demo that I did a little bit early that I'm going to skip over. So now let's go into the actual underpinnings. We're going to do a tour through kind of the subsystems, and then we're going to go right down to the kernel. So let's talk about some of the subsystems. So let's talk about container file systems. So if you're familiar with virtual machines, you're familiar with virtual hard drives. These are block-based devices. And what I mean by that is you have a guest operating system. It writes to a file system. The file system writes to a driver. The driver writes to what it thinks is a disk, and it's writing 0s and 1s. And the virtual hard drive represents the blocks, the 0s and 1s, and they get written. Now, the upside of that, the reason why we did that is it means we can run any OS with any file system. The downside of that is it is horrifically inefficient. We are horrifically dumb about what's running on top of us. We don't know what file system is running. We don't know what data is important or not. And the result is virtual hard drives tend to be large. And especially differencing hard drives are huge because we do differencing at the block level. And this is a real problem when we start looking at portability and speed. So containers have a great advantage for us. And the advantage is it's always going to be a copy of Windows in there. Because you can only run Windows containers on Windows and Linux containers on Linux. And so we know, hey, it's going to be NTFS or REFS. That's simple. And guess what? We have all the source code for that. So we know how to make that work. So containers aren't using virtual hard drives. Instead, we built the virtualization layer at the file system level. And when you create a new container, we lay down a set of files, and we track the changes at a file system layer. When you create a new container image, we're able to track the files that change, and we store the files that change. Now, there are a couple of results there, and there are a couple of challenges. The result is this makes container images incredibly small. One thing that I did just in my personal lab is I created a new container image, and I said, OK, let's install Minecraft. Set up a Minecraft server. I get that all set up, and when I'm done, I'm like, OK, let's export that. Let's see how big that is. I export that container. Now, to highlight, I have a Minecraft server in a VM at home. It uses 12 gig of hard drive for Minecraft. Same thing, running in a container, 150 meg. There's a huge difference, especially when you start thinking about, like, well, hybrid cloud scenarios. And when I want to move that workload up and down, it's just capturing the changes. So that's a huge advantage. One of the biggest challenges that we hit, though, and this is a really interesting difference when compared to Linux containers, is I don't know if you guys have noticed this, but Linux has a lot of file systems. They keep on making new ones. There's a lot of people out there who make file systems. Windows has 2. We've got NTFS and REFS. Now, there's an interesting architectural thing that happens here, and the interesting architectural thing is because Linux has so many file systems and users are able to switch them in and out, most of Linux doesn't take advantage of most of the functionality of the file system. Whereas Windows has NTFS, the big file system, and REFS, the new one, and NTFS, everyone takes advantage of all the little bells and whistles because why wouldn't you? And so when we started trying to figure out how to make a union file system, which is what you call it when you take multiple folder structures and merge them on top of each other, we started finding all these aspects of NTFS that just don't play well with that. We spent months beating our brains out on the fact that NTFS supports transactional file operations. Wonderful thing, if you're doing a production server. Terrible thing if you're trying to do file system virtualization. Transaction file systems allow you to start a transaction, do a whole bunch of file operations, and roll it back as an atomic operation. And honestly, we spent a couple of months trying to convince ourselves that we didn't have to support that. We were like really hopeful. We were like going like, come on, let's go. Let's just build the system without transaction support and see what breaks. Side note, if you build the system without transaction support, the first thing that breaks is Windows Update, which is a bit of a problem. The second thing that breaks is Windows role installation, also a bit of a problem. So we kind of wrestled through all of these. And what we ended up doing was we ended up coming up with a hybrid approach. And the hybrid approach was that we said, OK, for the pedestrian file system access stuff that is what 95% of what people do, we're going to do file system level virtualization. But for these advanced NTFS functions, we will create a small block device that we use for tracking that activity. And so that's what we actually have today. If you go digging through the file system, I'm not going to do this on stage because every time I do, I get lost. It's all under program data. So if you want to go in and mess with things and potentially break your system, go play around there. But if you go digging in program data, what you'll eventually find is you'll find a set of folders with really long names that contain all the file bits. And along with that, you'll find some really small virtual hard drives. These are usually a couple of meg in size. And they store the metadata. But that's not all we did. Because I talked about the speed and how fast it was to boot Nano Server. One of the things I actually loved about working on containers is the fact that I got to go and complain to people and be like, do you realize that your component takes a second and a half to start? And that's a problem. That's so much fun. And and as a side note, when we got containers up and running and functional, but when we started on the okay, these are functional enough, we need to start looking at performance, we were at about 10 to 15 seconds to start a container. It has been a long journey to get down to that 600 milliseconds. And one of the things that we found along that journey was, OK, the process for starting and booting a container is almost completely storage I/O bound. It's all about how much storage I/O we could do. And so we spent a lot of time looking at this and trying to analyze this and make this better. And one of the things that we found was, oh, if we're doing the Union file system with NTFS and you boot up Windows, almost immediately the first thing it does is write something to the registry. And the first thing we have to do is we have to bring the whole registry hive across to make a new copy of it. And so as part of booting every Windows container, we were making a copy of that registry hive. Well, that's not a small thing. And it added about half a second. So we went through and we did the work where we said, OK, we're going to build a virtual registry. And so now when you boot a container, it has its own virtual registry that's overlaid on top of a clean copy that we keep underneath that's part of the base image. So that as containers access the registry, we don't have to pull an entire copy of that in, and we're only keep track of the changes that it made. So the final thing to talk about on the file system front is the concept of base images. So we currently distribute two base images, the Windows Server Core and the Nano Server base image. These are signed by Microsoft. They are from Microsoft. And I've had a number of times I've had people be like, can I build my own base images? I was like, no, and you don't want to. Nor do you need to. So let's talk about you don't need to, and then we'll talk about you don't want to. So the you don't need to is when we create container layers and image layers. One, because we're doing this at the file system, they don't have any performance side effect like virtual hard drives where we're doing block mapping. It just goes to the file that it needs to go to, and there's no performance penalty to that. So you can have as many layers as you want, and on top of that, you can delete things from layers. And we have the technology where you can go in and start with the base image and delete a bunch of things. So whatever you want to do with containers, you can do on top of the official base images. The second thing, though, is a key part of the portability and the power of containers. And the reason why, when I export my Minecraft server, it's only like 150 meg, is because everyone in the world has the same 2 base images. And I need to be able to give you my 150 meg difference on top of that and know that you can pull down the same base image and run off of that. So it is a key part to the whole mobility promise. So now, that was file system. Let's talk about networking. Networking is really interesting. We do huge amounts of effort on networking. I'm going to put up a diagram that's going to confuse everyone, and I'm not going to talk about it for about 2-3 minutes, and then I'll get to it, and because I like doing that. Everyone's going to look at this and be like, that diagram doesn't make sense. Networking's been particularly interesting for containers. It's been interesting for 2 reasons. The first reason is, and this is kind of across the landscape, one of the challenges we had about doing container technology on Windows is Windows has a lot more components that straddle the user mode, kernel mode boundary. And when you think about containers, in many ways what we're doing is we're just running multiple instances of user mode on top of one kernel. And there's this interesting, we spent a bunch of time investigating this. So there's a lot more code that crosses user mode and kernel mode in Windows than there is in Linux. This makes it easier to do containers on Linux than on Windows. And we spent some time thinking, like, why is that? Is there like some architectural advantage that we're missing? Like, oh, what's the deal? And what the conclusion that we came to was like, oh, the reason why Windows has more code that spans the user mode, kernel mode boundary is because in the open source world, quite often, the people who maintain the user mode code and the people who maintain the kernel mode code are different people on different teams, and it's annoying to have to coordinate that. And so if you're working on a Linux project, you'll be like, if I can just keep this all in user mode, I will, because it's easier. Whereas at Microsoft, no. Like, it's all one team, and you just do what makes sense. Now, the challenge then becomes when we're doing containers, we had to go through and we had to identify, like, oh, here's a transition from user mode to kernel mode. We have to do work to enlighten the kernel mode component to be aware of containers. My poster child example of this on many fronts is DHCP, and specifically the DHCP client. And the DHCP client is interesting for 2 reasons. The first reason is this is a component in Windows that spans the kernel mode, user mode boundary. Parts of it run in kernel mode, parts of it run in user mode. In Linux, it's all in user mode. So we had to do work to go through and enlighten the kernel mode component so that they could have multiple queues and understand what's going on. The second thing, and this kind of comes back to my earlier performance comment, is did you know that Windows DHCP acquire takes 2 seconds? It's a really long time. So we had to do a whole bunch of work to figure out not only how to make these technologies work in containers, but to make them a lot faster. So hopefully some people have looked at this diagram and seen the obvious oddity, and they've gone, Ben, wait a second. You've just put up a diagram of a virtual switch. Are you sure you're doing the right presentation? You're doing a container presentation, not a virtual machine presentation. I've seen your virtual machine presentations. This is a slide from one of those. And the answer is, yes, I did put up a diagram of a virtual switch because we use the same infrastructure. And that was a very explicit decision on our behalf. we wanted to be able to, there's a lot of investment happening in the software-defined networking space. We wanted to be able to utilize that in containers as well as in virtual machines. We wanted to make sure that as we invested in technology for containers, it benefited virtual machines and vice versa. So we used the same infrastructure. However, we did make a couple of key changes. The first key change is we've extended the Hyper-V virtual switch to now have native NAT support. And by default, when you configure a container, we hook it up to a virtual switch that does NAT. Well, why would we do that? There's two reasons why we would do that. The first reason is because it's what everyone does on Linux, and people seem to like it there, and we want to have compatibility and similar offerings. The second reason is, I demoed just earlier creating a container, going like, yay, look, and threw it away. If I connected that directly to the network, which I can do, that is, you can go through and configure that, then I would have just grabbed a DHCP lease and thrown it away that quickly. Now, amusing story, the base team is notorious for being really hard on Microsoft infrastructure. We have there's a whole bunch of infrastructure where they've just put it aside and gone like, okay, like you base guys are crazy. We have our own virtual domain inside Microsoft. Most Microsoft domains are region-based. There is a domain called NTDev, which is not region-based, and it is for the base team so that we don't mess with other people's domain policies. And lots of stuff like that. Now, one of the things that they did a while ago is whatever building we're in, because we have virtual machines and so on, they go through and they change the DHCP lease policy to be an 8-hour lease. Well, when we started, we had a period when we were working on containers, and we didn't have the NAT networking technology up, so everyone was running ROAR, and we would exhaust DHCP in our building about 2 p.m. every day. And the best thing was, it took us a couple of weeks to figure out that was what was happening. We had a couple of weeks where every afternoon, it would get to around 2 or 3 p.m., and the developer mail discussion list would start lighting up with people going like, okay, who broke networking? All my tests are failing. I know it's not the code I did. Someone broke networking. And it took us a while to be like, oh, we're running out of DHCP leases. So that's the other reason why you want to use NAT. So we implemented NAT support. The other big change that we did is, while we use a lot of the core infrastructure from virtual machines, what we actually do is, in a virtual machine environment, we create a virtual network adapter, we attach it to a virtual machine, and the guest operating system gets stood up on top of that. When we're doing a container, we actually create the virtual network adapter and we attach it to the container host. And we stand up a large portion of the networking stack in the container host, and we actually transition over into the container much higher up in the networking stack. And the reason why we do that is for performance, in order to avoid really long network initialization times. So it's hard to observe that in the system. You can observe it in the system if you go poking around, if you go look at hidden devices in the system and try and find where all the virtual network adapters are at. To the average end user, you don't see it. The second thing I'd like to discuss on networking is Active Directory. This is something that I'm really psyched about. And the reason why I'm really psyched about it is because we made it work and we didn't believe we could. Honestly, if you had come to me a year ago and said, hey, Ben, by the time you ship Windows Server 2016, you're going to have made Active Directory work with containers, right? I would have been like, I wouldn't bet on it. In fact, I would say a year ago, about 3/4 of the core engineering team was like, this is not going to happen. Thankfully, we put a team on it, and they were like, well, we're going to try our hardest and see what happens. Now, we had this real challenge around Active Directory. On one hand, we know that our customers use Active Directory, they like Active Directory, and they expect it to work with containers. On the other hand, think about the 600 millisecond start. Let me tell you, that doesn't involve joining a domain. That's not really viable. And think about, I just talked about, we exhausted a DHCP server. Imagine if we created an object in Active Directory every time we booted one of those containers. You'd bring down domain controllers faster than you could believe. But on the flip side, if we look at what happens in the Linux community, it's really bad. One, the people who do it well just do it by managing certificates. How many people here like managing certificates? No one? Interesting fact. There is a quarterly meeting at Microsoft where we go over support call generators for Windows Server. For the last 4 years, every time the #1 support call generator has been people failing to manage certificates correctly. For the last 4 years, solid. So, okay, certificate management, bad. Do you know the other thing that people in the Linux community do here? It's really great. They hard-code in passwords into their containers. That's great. If you're looking for a fun evening activity, go to GitHub and search for Docker files that have the word password in them. You will find a lot. So obviously, that's all bad. So what we ended up doing was we ended up using some functionality that was built into Active Directory called the Group Managed Service Account. And the way this workflow works is ahead of time, before doing anything with your container, you go, OK, I have containers that need to access resources in Active Directory. They need to be securely authenticated. I'm going to create a set of group managed service accounts for them. And you can go check the articles on TechNet if you're not familiar with this. It's a handful of PowerShell commands to get it all set up. Then inside your container, for the app running inside your container, you say just go with default credentials. Just don't have user credentials. Use a system. Use system account, use local system, network service. When you start the container using Docker or using whatever managed tool, as you start it, you can say, associate this container with this group managed service account in Active Directory. And then whenever that container reaches out to a resource on your network, it will use that identity. So the great things about this, one, it allows your containers to securely access resource in your Active Directory environment. Woo! Two, it doesn't impact startup time at all. Three, you don't have to put any credentials or details inside the container. And that is super important when you think about the portability and the mobility. Because now, if you want to take that set of containers and run it in a different domain, run it in a different environment, run it in a different cloud, you don't have to change any of the artifacts inside the container in order to make that work. So I'm super excited about that. Thrilled that the team figured out how to solve that problem. So, memory. I'm not going to spend a lot of time digging into this. I do want to talk about, we did a bunch of work with the Windows Memory Manager. Unlike virtual machines, which the Windows Memory Manager has no insight into, the Windows Memory Manager manages the memory space for each container. We do have isolation technology that we built around that. But one of the key things is that there's this interesting kind of feedback loop on the file system approach, the memory manager approach, and the performance. So I talked about, we looked at container start time and container provision, and we went, this is all storage I/O bound. And so one of the key things that we did was there's a lot of the initial Windows boot, which is booting off of read-only kernel mode components. Nothing changes a lot of the core Windows kernel that gets booted off of. So what we were able to do was we were able to enlighten the memory manager so that when we start up a new Windows container, as it boots, it goes, OK, can you load that file off disk? That goes to the host memory manager, and the host memory manager goes, I've already got it here in memory. and it just points the container to that. And that's a large part of how we get the really fast boot, is that the memory manager is able to go like, oh, I've got an unmodified copy of that already in memory. Let's just stitch that up and use that. Now, as things get modified, the memory manager makes copies and does all the appropriate sanitation on that. But for a lot of the core Windows components, they don't get modified as the operating system runs. So now that we've covered the nice high-level stuff, let's go even deeper and talk about the changes to the kernel. And this is where I'm really going to dig into a lot of the places where Windows containers and Linux containers start diverging significantly. We had to do a bunch of work inside the Windows kernel to build this concept of a separated user mode space. Now, if you're familiar with Linux containers, you will have seen when I started that nano container before and I said, get process. And you'll be like, there was a bunch of processes running there. When I run a Linux container, I don't have that. I just have the process that I'm running. So every time we start a container, we start SMSS, which for the Linux nerds, that's pretty much the Windows equivalent of initd, but no one ever talks about it. But that's essentially its role. And we start a core set of services. And why do we have those services? Well, in the Linux world, the approach that the Linux world has taken is they've gone like, OK, we have a set of syscalls. And we're going to change those syscalls all the time, because that's what kernel engineers do. And those changes will often be breaking. But that's OK, because anytime we make a breaking change to a syscall, our advice will just be, well, rebuild everything. And then it will be fine. And that's what it does. And I mean, if you've ever used Linux and you've had a non-open source kernel module on there, you'll see all these error messages and screaming, going like, oh my goodness, like you've got something that's calling kernel APIs that isn't open source. This is going to break. That's why. Now on the Windows side, we don't have that. We document APIs and we maintain that API layer so that you can run different components on top of it. And as we change the kernel, it doesn't break you. So how do we achieve that? Well, we achieve that through these services. And basically what we do is when we have kernel APIs that we know we're going to be changing, we create a Windows service that provides an API access point to them. And so the result is that in the Windows world, there's a core set of services that if you don't have them, not much runs. And so we've done a bunch of work to identify what the right set are, but every Windows container has a core set of services. And that then builds on top of what we call a silo. And this is, I'll show you what this looks like in a little bit. Now, if you're used to the underpinnings of containers on Linux, they talk a lot about namespaces. Linux is a lot more decoupled system than Windows, because quite often the different subsystems are built by people who don't talk to each other very much. They're in different locations and so on. And so namespaces in Linux is a way for them to deliver this isolation technology kind of piecemeal. On Windows, all of this is developed by one team that works very closely together. And silos are basically a way for us to take everything that makes up a user mode space, so the registry, the process IDs, so on, and separate it out. So I'm going to skip over this slide, and I'm going to show you what this actually looks like in person. And this should be fun. So first thing I will disclaimer, in order to do this demo, I am going to use some internal tools that only I have access to, and no, I'm not going to give them to you. So sorry, you're just going to have to watch the demo and enjoy. So there's a fun thing about Windows that I find amusing and will make half the people in here with a Unix, Linux background really angry. And that is, if you ask people, what's the difference between Windows and Linux, one of the things that usually comes up is the whole like, well, Linux, everything's rooted in root, /, and Windows has this crazy C drive, D drive approach? Well, the reality is that in Windows, everything is rooted in backslash. So I have a tool here that we have internally called objdr that allows me to see the construction of the system as it actually is. And if I look at this, this is the global root from the system. This is actually what the system looks like internally to the kernel. And you're going to notice that everything is rooted in backslash. And if let me see if I can find my C drive. This is really hard to do zoomed in. I should never zoom in to do this. It'll be one of these. Nope. Here's my C drive. So C drive, that's actually /device /hard disk volume 4. And if I go digging through this, there'll be stuff that's very familiar to people from a Unix background. For instance, there's my mail slot. My favorite one is somewhere in here, there is /dev/null, because of course we have one of those. So at a core kernel structure, we have this object namespace where everything is built. Now, if I go digging through this, what you're actually going to find is, I'm going to zoom out so I can find this easier and zoom in later on. Where are we? So somewhere in here, we have the namespace for silos. There you go. So if you have a look at the object store, you'll see this /silos. So why is that important? And this is so a question that I've often got is, hey, you talk about Windows containers being a separate user mode space. Are they any more or less secure than just running separate processors? And the answer is they're more secure than running separate processors, but not as secure as virtual machines. And let me show you a key difference here. So I'm going to start up a container, and I'm going to stick a copy of my tools in there so I can show you what this looks like inside a container. So if I run my tools here, you can see, wait a second, that's a much simpler object structure. And what we actually do when we create the container is actually a construct built on top of the silo, which is the core bit in the kernel. When we create the silo, we first create this lightweight structure in the global object structure. So if I were to go back and look at my host now, there would be about, how many entries do we have? There would be 21 extra entries in the table. And they would all be hosted under that silos area. So this is where kind of the extra level of isolation comes in, because now if a process calls into a kernel mode API or a kernel mode service, rather than getting access to the root one, it's getting redirected to this jail, this silo in the object space. So, fun to show, and yes, you'll never get that tool. I apologize. So we've talked a bit about how these are all pulled together and how we do the isolation under the covers. Now let's talk about Hyper-V containers. And Hyper-V containers are a really interesting story and a really interesting history. So when we started working on containers, fairly early in the process, we had the discussion about are we going to use a hypervisor for this, or is this going to be just a pure kernel construct? And actually, early in the process, we were like, we're just going to do this as a kernel thing. We're not going to use a hypervisor. That decision lasted for about 6 weeks because we had a really interesting thing happen. And that was, as we were working on this, we're talking to different teams inside Microsoft. We're talking to teams in Azure. And they were really excited about Windows containers. They were like, oh, this is exactly what we needed. Like, OK, fine. And a number of the teams in Azure, Azure Automation, Azure Machine Learning, have been some of our first and best customers as we've been building this. But as we were talking through, one of the things they were very quick to say was like, oh, wait a second. you're not using a hypervisor for this. And we're like, no, this is just a kernel construct. And they're like, great, we're not using it. And we're like, what? And they're like, no, you don't understand. People try and hack us every minute of every hour of every day. If you cannot provide guaranteed isolation at a hypervisor level, we're not using it. And this caused us a lot of grief. And like in full disclosure, there was a period of time where we were going around going like, yeah, we're doing Windows Server containers and Hyper-V containers. And on the engineering team, we're like, how are we going to make Hyper-V containers work? We're like, we don't know. We'll figure it out. We're like, it has to be possible somehow. But we always had this goal with Windows Server containers and Hyper-V containers that we're like, okay, what we want to deliver is we want to deliver something that has 100% compatibility with a Windows Server container, but provides the isolation guarantees of a virtual machine. And we've been able to achieve that. And one of the really cool things to call out here is the decision to run in a Windows Server container or a Hyper-V container is actually a runtime decision. You can run a workload in a Windows Server container, stop it, start it as a Hyper-V container, stop it, start it as a Windows Server container. Why is that important? Well, that's important because it comes back to the portability story. In one environment, you might prefer Windows Server containers. In another, you might prefer Hyper-V containers. Here's a fun one. I spent a bunch of time researching. I do a lot of user research. That's what I do. I love going out and finding out when people do things that make no sense. And going back and telling my team, like, hey, here's what people do. And they're all like, no. Yeah. So here's a fun one. And I know this will shock the room. Most developers do not think about security when they're building their project. I know, newsflash. But this is really interesting, isn't it? Because it's an interesting challenge around like, if we didn't have this portability between Windows Server containers and Hyper-V containers, that developers would build all their stuff on Windows Server containers because it's easier. And then the ops guy would be like, damn it. But fine. We built it so that whatever the developer does doesn't change what the ops guy does. And the ops guy can decide independently. He can decide, you know what? This workload needs the security protection of Hyper-V. I'm going to do Hyper-V containers. Or he can decide, this is just internal facing. I'm going to use Windows Server containers. That is a deployment time decision. So from an architectural point of view, what does this look like? So if we have this diagram, which is kind of what Windows Server containers look like. We have our Windows kernel, we have our management components, and then we have these silos with job objects, the network interface, the storage, and the processes running on top of it. With Hyper-V containers, we run this all in what is, in essence, a highly optimized virtual machine. Now, this is a virtual machine that you never get to see. It's actually a read-only virtual machine, and it is custom built for the purpose of running a single Windows Server container. And we did that for a couple of reasons. The first one was we wanted it to be as lightweight as possible. We wanted it to add as little overhead to the process. The second reason was we wanted to make this thing as secure as possible. And so by making it read-only, one, it's kind of hard to hack something that's read-only. Two, every time you start a Hyper-V container, you get a new image. Three, it also makes it really easy for us to keep that up to date. If there's ever something that we have to service, we just service that quietly through Windows Update. And next time you start a container, you get a new one. Now, we did a bunch of work. We got this. We do have a version of Windows that runs in the container. We were hopeful that we'd made the smallest version of Windows yet, but we hadn't. We did some research. So the copy of Windows that runs inside a Hyper-V container is about 40 megabyte in size, but it's not actually the smallest one. we boot this up. We use the same networking stack that we do for Windows Server containers, because it's the same networking stack we use for virtual machines. For the file system, this is kind of interesting. We use the same file system infrastructure in the host operating system, and we expose that into the container by doing SMB over VMbus. So we get some really interesting performance from that. Now, we did a bunch of performance tuning on this, but there is still overhead to running a Hyper-V container. If you go back to the beginning slides in this, I showed that I had the numbers up there where a Hyper-V container does take a bit longer to start. It does use more memory. So there are trade-offs. One of the interesting things, though, when we were first working on this, we came up with this idea. And the idea is a technique that we call cloning. So I talked about how in Hyper-V containers we're booting a custom version of Windows that is read-only, you can't modify, you can't change. What this actually means is that every time you start a container, a Hyper-V container, the first chunk of booting is the same. It's only once you actually start the Windows Server container inside that custom VM that things start to get different. And so what we actually do is, and we do this dynamically, and we do it dynamically so that we can patch and update and so on. Every time you boot the physical computer, the first time you start a Hyper-V container on that system, we start it up clean, and we boot through it. But we have identified the exact point in that boot process where we're just about to start running differentiated code. And just before that, we go, quick, take a snapshot. Make a copy of this. And then the next time you start a Hyper-V container, we start from that. So the net effect of this is, I'll see if I can show this to you. Disclaimer, last time I demoed this on stage, which was last week, this demo failed. So we'll see how this goes. The net effect of this is that the second time you start a Hyper-V container, it's a little bit faster. So I'm going to copy this command. And then I'm going to zoom in. So, and I'm going to remember, I always do this. I haven't exited this container. If I forget to exit that container, I start trying to run containers inside containers, and it all breaks. So just make sure I don't have any containers running. So I have 3 images. I have my Nano server, my core. I have an IIS image that I built ahead of time. So I'm going to use that IIS image. So first thing I want to do is I just want to show you the speed for running this IIS image as a Windows Server container. So I start it up, and it's running. It's pretty darn instantaneous. And right now, that IIS image is running in the background, is providing a web server. So I'm going to stop that. Now I'm going to come over here, copy this again. Now I'm going to run the exact same image, only this time I'm going to do it in a Hyper-V container. And this is going to take a little bit longer. We're doing the boot of the virtual machine for the first time, and we're creating that base image. But the key thing to understand is, this is the full portability. I can switch back and forth between the two. So if this demo goes well, it should be done any second now. This blew up on stage last time I did this, and it did a bunch of text all over the place. So there we go. So that took about, I'd say, 5 seconds-ish. But I have it running here. Let's stop that. But now if I try and do that again, it's going to be substantially faster because we have the cloned image in memory. So you can see that was about 2-3 seconds this time. And so the first time you start a Hyper-V container, I do just want to highlight a couple of things. If you see this command, P8080, that's me mapping the port through. And to show that all of this is not smoke and mirrors, let's grab this IP address. And I actually have another virtual machine over here that's on the same network. And there's my web server. So, with all that said and done, we are at exactly time. Look at that. So, I would like to thank everyone. I hope this has been informative. And I would love people to ask questions. You're also free to go. I believe the Hub Happy Hour is starting, which I'll be wandering over to. But thank you all for your time.